Поехали. Ну, я надеюсь, что меня слышно, да? Это... А, вот как раз, Леонид, вы проверяете, да? И что оказалось? Помехи опять, господи. Я говорю что-нибудь. Все равно плохо слышно? Тест. Нормально? Ничего. Годится. Хорошо. Окей. So, thanks. So let's start. Last time we formulated the main theorem that maybe I will not repeat the whole formulation, but just say that the functor quad, depending on the choice of variable line bundle and some coherent sheaf on some projective scheme over the base. So this is representable by a projective scheme without underline. Okay, so I hope we will prove this theorem today, finally. We start with the first reduction, namely to the case when X is the whole projective space and E is vector bundle pulled back from the base. So we consider X is a projectivization of some vector bundle over S. And again, the most common case is when S is just a point. Okay, so then it's just the projective space, absolute projective space. The coherent sheaf is the pullback of some vector bundle on S. And again, in this most common case, it's just a trivial vector bundle on projective space. So pi is the projection from this projective space to relative projective space to the base. We have to prove this. It follows from a lemma that first of all, for any integer, the twist by this integer establishes an isomorphism of two quad schemes. So have rather quad functors. Yes. That's what I'm proving now, or at least for formulating. So here we just twist by L to the power nu. What is L is a choice of variable line bundle on our variety X.
This reduction is arbitrary.
yeah, here we don't need it. So here, phi and psi are related just by the shift. Psi of lambda is phi of lambda plus nu, and we twist by nu, and this is absolutely evident. There is nothing to prove. And second, so say let we have a surjection. Yeah, except for phi and psi in the upper index. Yeah. The underline is missing. Yeah, thank you. Thank you. Yeah. So suppose we have a surjection phi, and this is a coherent sheaf on X. Then we have a natural morphism of our quad functors from H over X over S. No, absolutely. No. No. Why? Like this. And this embedding of functors is a closed embedding. I will say in a moment what does it mean. Okay, so this is the statement of the lemma, and it will imply what I said, because we can represent any X as the quotient of the structure sheaf on the ambient projective space, and then we can represent any coherent sheaf over X after a high enough twist like this by of 1 million as a quotient of vector bundle. Okay, so this will suffice. And then what does it mean, and why does it suffice? It means that for any test scheme T over S, and a family F and Q in the quad scheme of E over X over S. Okay, so this is some presentation as a quotient of E in the pullback to T. Okay.
Phi is surjective.
Phi is surjective, yes. So for any quotient over T, there is a closed subscheme T prime in T with the following universal property. So now I'm formulating this universal property for any, well, so to say, test scheme now over T. So test scheme was over S. Now this double test is over T. um, the pullback QU from EU to FU. Factors through T prime, sorry, through phi u. This is our surjection, like this, yeah, the pullback. If and only if our gamma factors through u to t prime, like this. Okay, so pardon me? Well, I don't know. Maybe there is nothing much to draw here, but I just mean that, like, if we believe that our functor is representable by a scheme, like t, for example, if this t is universal, if it represents the functor, then the other functor is represented by a closed subscheme. That's what I want to formulate. And you can formulate it somehow abstractly without even representability. Okay, so the property of an embedding of functors can be a closed embedding without being representable. So we know what is closed embedding of schemes, and then it defines something on the corresponding representable functors. But you can define this property of representable functors more generally, even before you know that they are representable. But then eventually we'll prove that they are representable, and the fact that this is representable will imply that that is representable. So somehow this is for like P n.
This is a test scheme.
Yeah. But still, for any test scheme, you have another test subscheme.
As I understand, we want this quote functor to be representable.
Yes, but I claim that it's enough to prove representability for some basic case, when our variety is the ambient project space and when our coherent sheaf is just the vector bundle pulled back from the base. And then from this, the representability will follow by this general nonsense, but I didn't prove, I only formulated lemma so far, I didn't prove it. Maybe if I prove it, it becomes clearer.
Just too fast.
I mean that this embedding of functors is a closed embedding in this sense. Maybe I shouldn't formulate it this way. Maybe I should just say what I need. So assume that that this is representable. Okay? Assume this functor is representable by quad without underline. Then this functor will be certainly representable by some closed subscheme. I didn't prove this yet. I will prove this in a moment. But so we need just the following corollary. if quad E over X over S is represented by some scheme without underline, then the subfunctor H over X over S is represented by a closed subscheme. Well, that will be just quad without underline. So that's what we need to prove. And maybe I shouldn't even state it this way. The only thing is that towards the end we will need, again, some property of representing functors, or something like this.
You mentioned the abstract nonsense, so is it the case that this is true in more general situation for
So you don't need these functions to be representable. If your functor is representable, then I mean nothing else. I just apply this. Yes. So I just want to say that there is a notion of closed embedding of functors. That's all I want to say.
works in any category.
Well, as you see, you need, these are functors on the category of schemes, and on this underlying category, you need the notion of closed embedding. If you have some category with notion of closed embeddings, then the functors from this category to sets also inherits this notion of closed embeddings. That's all I am trying to say. Sorry about this. So we still have to prove this claim, and this claim is evident. So proof is much, much shorter than the statement of the lemma, just one line. Namely, T prime is the zero subscheme, or zero, I don't know how to say, it's not zero divisor, but just zero subscheme of the composition morphism the kernel of phi is embedded into E and then projects to F. Okay. And that's just a tautology. So I mean, if this composition is zero, then certainly the morphism phi u factors through H. Okay, but by definition.
What is the map from HU to FU?
The induced one. So you have E, it goes to F. On the other hand, it goes to H. Okay, and if it happens that the kernel of this map is contained in the kernel of that, then you have then it factors through such a morphism. Okay. So there's just absolutely nothing to prove. It's for free. Fine. So we reduced our theorem to this basic case, and now we are considering this basic case, and we apply all the science we developed last 2 weeks. So we begin with Mumford theorem that you used notion of regularity, and it said that well, it gave some a priori estimate on the twisting that ensured regularity. Well, if you okay, let me formulate it, and then we'll see what you remember. So X is now projectivization of this vector bundle. E is the pullback of another vector bundle. L is just of 1. Whatever the rank of V is n plus 1, so it's relative Pn, so to say. And we know that for any fiber, the restriction of E to this fiber, which is just projective space Pn, so to say, is O Pn to the power P, where P is the rank of that other vector bundle. Okay, and this Mumford's theorem guarantees that for any Hilbert polynomial, there is some integer big enough which depends only on this phi, on p and n, and nothing else, such that for any fiber the restriction of our sheaf, well, many. This is just the trivial sheaf, the trivial vector bundle, and I am saying nothing about this, but I will continue. So M regular means that the higher cohomology of Pn with coefficients in your sheaf twisted by, or maybe I should say ith cohomology twisted by m minus I is 0. If I'm not mistaken. Yes, ith cohomology of m twisted by m minus I is 0, and that's yes, absolutely. So this is here is nothing to prove, but also for any surjection Q from E to F with Hilbert polynomial of F equal to phi, the kernel and the quotient so both E and F are also M regular. Okay. So that is what we proved for 2 weeks ago. Well, maybe we proved just for the kernel, but then in your exercises, if you know for 2 sheaves in short sequence, then you know for the third one as well. Okay. So we know that everything is regular, and again by the exercises, by today's exercises, by the way. Today's exercises, it follows that for any r bigger than m, we will have a vanishing of all the higher cohomology. Okay, and all these guys, so ES twisted and FS twisted and GS twisted are all generated by their global sections.
Again, what cohomology is,
Oh, sorry, positive, yes. All the positive cohomology vanish, and the zeroth cohomology generate the sheaves. By what? I mean that there is a canonical morphism from the structure sheaf tensored by the space of global sections to our sheaf. Yeah, just, well, if you want evaluation H0 of X with coefficients in arbitrary sheaf H, tensor OX maps into H. Yeah, just evaluating at all the points, if you wish. Yeah? And I say that this is surjection. Then H is called generated by global sections. Well, so H0 of X with coefficients in H is nothing but a home from OX into H. Right? And so you just evaluate. Okay, so we know this, and then we apply Grothendieck theorems or theory, I don't know. Well, about semi-continuity, and Bayes extensions, or Bayes change. Okay, and what we get is the following information. So for any test scheme, this will be our Bayes change, T over S. and any OT flat quotient sheaf this with Hilbert polynomial equal to phi, and G the kernel of this Q, so it's inside ET. The following holds. The sheaves the push forwards to the base so we have PS and goes to S, there is this base change, and we have P and T goes to T, and this is called pi, or maybe pi S, and this is called pi T. Okay. So all these guys are locally free. Of the ranks depending only on N, P, R, and phi. Okay. Also, we have the generation by global sections, fiber-wise, along with base change. So if we pull back the push forward, so for each particular fiber, this will be the trivial sheaf. I already raised it. It's just multiple of the structure sheaf with coefficients in the global sections on this fiber. Yeah. So I say that this sheaf on each fiber is globally generated by its global sections, and the same in the family, and for all of them. So sorry. Subjects onto R, and the same with F. Okay, and the higher direct images of these projections vanish. Okay, so yeah, we just pull back everything to maybe I should say ET here, yeah.
F is flat for S.
Mm-hmm. But everything is flat. We will pull back to T for any base change. Yeah, like here.
First the F is flat over OS and then flat over OT.
Right. It's pulled back as flat over OT. Yes. Mm-hmm. So the high direct images of this vanish, and the same for this, and the same for F. Okay, and what else? Well, this was all for any R bigger than M. That's still in. The assumption still holds. Okay. Yes.
Suspension is because it's fiber-wise zero.
It's fiber-wise zero, and also there is the base extension or base change isomorphism, if you remember from a month ago. So we can either first restrict to the fiber and then take push forward, or else we can take this global push forward and then take its fiber, and that's the same. So due to this, what you say is true. Okay, so now, let me erase this. I want to keep too many things on the blackboard. Sorry. But we are close to our victory. Okay, so and also we have a commutative diagram like this. So these are two short Z sequences.
Can we write the second row in the row or the first?
The second. No, not necessarily. Well, there are long Z sequences. Maybe if you know two, then you will know the third. But it's not suffices to have one. But
long sequence of 5 direct images.
yes. So
For t it is 0. Then for
if you know the two are 0, then the third is 0 from long Z sequence. But doesn't matter. You know for each of them for the same price.
they are all
They are all totally 0. Yes. Everything is 0. Okay. So we have this exact sequence, and we have the quotient sheaves from here, and this is all compatible.
So that's just because of the branching from
Yes. Okay, so there is this commutative diagram with exact rows, and the upper row is locally free on X, on our on XT, on our project space over T. Yeah. So this all lives on XT. Okay, we pull back everything to any test scheme T, like that. Okay.
why are they locally free?
Because these are locally free, and then you just pull them back. So the lower row is locally free over T. Okay? So, well, sorry, what am I saying? No, this is some nonsense. I'm sorry. I mean, if I consider this push forward, just this part, this would be locally free over T. But then I pull it back to project space, and it's locally free over project space. That's what I say.
What does it mean for a shift to be locally free over the empty space?
But, for any scheme, you certainly know better than me what is locally free.
Yeah.
That's what I say.
It depends on the structure shift. I mean, you're saying that it's locally free?
Over the structure sheaf, yes. Yes? Because they live also on the same project space, not on the base. But well, just this lives on the base, but everything else lives on the project space. Sorry. Fine. So, yes.
You know the exactness for push forwards, and then you pull back. Then
Yes.
why the exactness still is?
But it's just a projective vector. Well, projection P and T goes to T. It's a smooth morphism, so any exact sequence is pulled back to exact sequence. The pullback is exact. It's a flat morphism, but smooth morphism. Okay, so that's where we are standing. And from here, we will deduce the desired property of quad functor. Okay? And in a sense, we're almost done. So from here, it will follow very quickly. So now fix one particular twist big enough so that all of this holds. Yeah. And then we know that there are no higher cohomology, so the rank of the push forward is given by the Hilbert polynomial, because there is no higher cohomology to contribute into Euler characteristic. If we compute the push forward of the trivial vector bundle E, right? Well, so E was just pull back of some vector bundle on T, yeah, well, pulled back from S. So on each fiber, our E is, on each projective space fiber, our vector bundle E is trivial. Okay? So we can compute the direct image of its twisting. Namely, what we get is just this very vector bundle tensor R symmetric power of the other vector bundle. Well, maybe like this. Okay? Yeah? Well, once again, it's trivial, so you can extract this factor, and for the structure sheaf, you know that global sectors of O of R is just symmetric power of the corresponding vector bundle. From this, it follows that the projection from pi t push forward of this onto the push forward of f of r defines an element in the relative Grassmannian. functor over W tensor symmetric power of Vs. So this is the ambient, well, relative vector space, so ambient vector bundle, and the quotient is of dimension phi of r. So once again, we have this, if S is a point, it is just a vector space, right? Some big vector space. I consider all the quotient space of this dimension. Quotient vector bundle of rank phi of r. Okay? But we know that this Grassmannian functor is representable by Grassmannian space, fibration. Again, over a point, it was proved in some exercise, like half a year ago, and over the base, it's just a relative version of the same exercise. Yes. The statement is that you have some vector bundle, like, and you have its quotient of fixed rank, like this.
R is a variable.
Well, we fixed some regular R, for which everything like this holds true, and then in particular we obtain some quotient vector bundle of this vector bundle, and this vector bundle is explicitly known. But again, it's enough to think of S just a point. Then it's just a vector space, and this is just some quotient vector space of dimension phi of r,
Yes.
and nothing else. So we obtain a point of Grassmannian.
Yes, and you say that we did some exercise.
In this exercise, a long time ago, you proved that the Grassmannian functor is representable by a Grassmannian scheme. Namely, you constructed some variety whose points were just vector subspace or vector quotient spaces of given dimension. And the same works in relative situation over the base, if you wish.
Representability of this.
Yes. So namely, you glue it from a fine patches, the big Schubert cells, whatever, and you never use Blücher embedding. Well, we will use it in 20 minutes, but so far, to construct Grassmannian, you don't need to know that it's projective. You construct it as a scheme, as a variety, and you never, well, at least so far, you didn't really ever need to know that it's projective variety. Some variety.
In the exercise, we were asked to determine our way by ourselves.
Yeah, but there was absolutely no need to use projective embedding, Blücher projective embedding. Certainly, you might.
It is useful to.
I know that it's useful. Yeah, believe me, I know that it's useful. But yes, I do know that it's useful. But so far in our life, it was useless. Today, it will become useful. But so far, there was no use for it.
I have a question about this phi t is
Yes.
E t of r equals to w variance.
Here.
Why is that?
But you remember what is E and what is P? Was a projectivization of this vector bundle nu S, and E was just the pullback of vector bundle WS. And here you just replace S by T. But then I think you can prove this as an exercise, for example. But it's absolutely evident.
This R is existing. Yes.
This R is the same R as here. Yes. 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 Okay. So somehow here is the key point of the whole argument. We constructed a morphism from this quad functor to Grassmannian functor. So we constructed a morphism of functors alpha from quad to GR. Okay, and that's what I promised a long time ago. Now, a long time ago, it was absolutely unclear if it was useful at all. I mean, I plan to explain that now that alpha is an embedding, and that's the key point. But it was absolutely unclear why on earth it would be an embedding. But now we're in position to prove that it's an embedding, and then closed embedding, and then we are done. Yes.
Don't we need mu t to the power minus 1? I mean, is this metric over R?
Yes.
Yes.
For example, if you twist by 1, well, take global sections of, then you just get V, right? Or maybe V star rather, but I hope it's. Maybe you say that I should take dual, yeah? That's what, yeah, sorry. Okay, yes, this I agree with. Yes. Yeah, absolutely, yes. This I agree. Okay, so now we did construct this morphism of functors, and what remains to check that it's an embedding and a closed embedding. So it takes alpha of this is the quotient like that. Again, this is our key construction. And the next claim is that alpha is an embedding now I hope I can erase this. And we only need this diagram. So if you contemplate this diagram while I'm erasing, you see that what we are interested in is this, right? Well, up to twist. The twist can be untwisted. That's no big deal. But what we have is that. Yeah, we have this. Well, we can pull it back to project space. So we have this. But we want to reconstruct that. That's our problem. So we want to reconstruct this lower line from the upper line. Okay. Let's take the universal exact sequence on the Grassmannian. we'll have the universal exact sequence. This is the functor, and this is some scheme representing this functor. Oh, sorry, yeah, thank you. Yes, this is the morphism of functors, and it's an embedding as a morphism of functors. Thank you. Okay, so the universal exact sequence. 0 goes to the universal kernel, goes to the universal, well, so to say, trivial bundle, goes to the universal quotient like this. So here, this Grassmannian scheme over S, this projection. Okay, and the upper row, as I said, is the pullback by T goes to the Grassmannian of this guy. Okay, just by the construction. And pardon me? Who is Q? And where is Q? Yeah, the universal quotient. The universal kernel, universal quotient. Right? The universal exact sequence, well, this is our projection to the vector bundle of fixed rank, and this is the kernel, so it's a vector subbundle of fixed rank and corank, whatever. Okay, so we know this. Now set H, the composition. Goes to E of R, and then goes to E of R itself. So it's this composition. Okay? Pardon me? Here. Thank you. Okay. So from this diagram, we see that the sequence, but without zero, so it's not necessarily an embedding. Goes by H into ET of R, goes by Q twisted by R to F twisted by R, goes to 0, is exact. So I go this way. So this is not an embedding, but well, from the exactness of both rows, you know that this is exact. Fine. So it's an exact sequence, and hence the our object of interest is nothing but the co-kernel of H. Okay, and finally, untwist by R. So after twist by R, we obtain this, the desired quotient as the co-kernel of this morphism, and then untwist by R, and we're done. So this was the key point. So we embedded our quad into Grassmannian. Now the only thing that remains is to check that this embedding of functors comes from an embedding of schemes, so it's sort of representable. Yeah, this functor is representable by Grassmannian, and we have some subfunctor, but we don't know. In principle, in a representable functor, you may have some weird non-representable subfunctor. There are many subfunctors, so we need some criterion for representability. And then finally that it's a closed embedding. Well, I just claimed that this sequence that starts upstairs but ends in the lower row is exact. Is right exact, so to say. Yeah? It helps to reconstruct, well, once again, we need to reconstruct this from that.
We get a suggestion.
Huh?
We get a suggestion.
Yes.
And why it needs this?
Once again, I need to reconstruct this from that. And I say that this is just co-kernel of this composition. That's it.
Now you want to untwist?
Yes?
Why?
Well, because initially, my quad functor is about quotients et goes to f. But instead I used this twisted et of r goes to f of r. But it doesn't matter, r is fixed. So in our...
You just construct a morphism of function,
Yes. Mm-hmm.
not claiming that
But then I claim that it's embedding.
you didn't prove it.
Yes, I did. Because I constructed this Q. I wanted to construct Q from the data on Grassmannian. And I succeeded. This is my data on Grassmannian.
Yes.
Well, this one. It's just the universal subsheaf. Yeah, it's pullback of this. And from that, I can reconstruct it as just as a co-kernel of H. So my f is a quotient of Et, but it's a quotient of Et by something. So I need to explain what is the quotient by. I say by the image of this morphism. That's it. So this is the key point. Okay, but to apply it, we needed to take a very high twist R, and this was achieved by the use of Mumford theorem. So here we use some boundedness, because for each particular sheaf, we may take some R. I mean, for each particular quotient sheaf, we may choose some R. But Mumford's theorem is infinitely stronger. It says that there is some R which is good for all possible quotients, not just for one. Some very strong boundedness, finiteness theory. It was initially proved by Grothendieck, but by some other argument, and Mumford's argument is shorter.
And what's the idea of Grothendieck's proof?
I don't remember. I read it like 30 years ago and forgot since then. I'm sorry, yeah. Okay. Also, there was some psychological thing that I didn't. It's in French, and I didn't really know French at the time. So I was learning French while reading this paper by Grothendieck. And then there was some psychological substitution. So when I succeeded in understanding just French grammar, I psychologically thought that I understood mathematics, which is absolutely wrong. So, but at least I understood something, at least French grammar, yeah. Okay, so we formulate and prove the, so to say, relative representability of alpha. And again, just as it was here an hour ago, the formulation will be rather long, and the proof will be one short line. Okay, so the statement will be much longer than the proof.
We are finished proving this theorem?
No, we construct an embedding of our functor into some representable functor, and we need to check that this embedding gives rise to some subscheme in Grassmannian, and not just a subset of representing functor, but actual subscheme of the representing scheme. Okay, and I will say what we need to check at the level of functors, and then it will be immediate to check it. Okay. So it means that for any test scheme T over S and morphism F from WT tensor symmetric power of T onto H. So H is a locally free OT module of rank phi of R. And there is a locally closed subscheme T prime in T with the following universal property. And the key point is here, that just as before, that there is a locally closed subscheme. It's a sort of, again, test, something for test. Now I wonder if I can erase this. Yeah, I guess I can. Well, the formulation and the proof will be very, very similar to reduction lemma, yes. Mm-hmm. Yes. Sort of, yes. Well, but we will be not able a priori to see that this is a closed embedding. We first have to check that it's a representable embedding, and then we will check that it's closed. No. In this situation, we didn't prove yet that alpha is a closed embedding. We're in the process of proving this.
Prove that it is embedding.
Just prove that it's an embedding, and now we're formulating the statement that it's a closed embedding. But only in the very end we'll be able to see that it's a closed embedding. First, to prove that it's a representable embedding. So there is a locally closed subscheme T prime with the following universal property. So for any test scheme Y over S endomorphism phi from Y to T, and they both live over S. We said Fy is the pullback of F to Y, and yes. Well, we yeah, if you wish. So this was the image of alpha, or dually the quotient from E of R, the pull push from E of R to F of R. Okay. So we pull back this universal subshift. So this is the kernel of Fy. This is the same as the pullback of kernel of F. And again, let pi y be the projection from our project, the pullback of our projection. Like this. And H is the composition. So I'm just rewriting what we had here, but in the pullback to some test scheme. Okay, the composition from the pullback of the kernel to pullback of W tensor nu Vs, sorry, systematic power. And this is this. Like this. And finally, Q from EY to F is the kernel of H, well, untwisted by negative R. And then we claim that F is locally is flat over Y with the Hilbert polynomial equal to phi. If and only if our phi here factors through this embedding. Okay, so we just essentially repeated, as Sergey says, what we did here an hour ago. Yeah, so we formulated our moduli problem about quotient sheaves with the fixed Hilbert polynomial, and we said that this moduli problem over arbitrary test scheme T factors through some subscheme T prime, okay, which is locally closed. Okay, so once again, I just repeated what we had here before. Before we had some closed scheme, subscheme. Here we have some locally closed subscheme, and that's the only difference. Okay, I just repeated the definition of locally closed subfunctor. Okay, I didn't prove it yet. I formulated it, yes. But I just succeeded with the formulation in this case. Now I have to prove it. And the proof is just one line, as I promised, because this is just our property of flattening stratification. It follows from our theorem about flattening stratification. So there we claimed last week that given sheaf on a scheme T, there is some stratification with universal property that is at the level of closed points. It is given by just the Hilbert polynomials of fibers, okay? But it has this universal property that any flat morphism factors through the disjoint union of strata. Yeah, last week there were two main theorems, Mumford theorem and this flattening stratification theorem. Well, maybe you look it up at your leisure time. And there we are. So we take T, the Grassmannian of W tensor symmetric power of V with phi of R, as we did, and with universal bundles like there, U from sorry, like this, okay, and get from this Q the subscheme T prime as well, the stratum of the flattening stratification well, corresponding to the Hilbert polynomial phi. Okay. Okay, so there we are.
Would it be empty?
Absolutely, yes, certainly. Certainly, if you take some stupid polynomial, for example, the one which has non-integral values, or that has non-positive values for big. So there are many polynomials that cannot possibly occur as Hilbert polynomials. Or if its degree is bigger than the dimension of ambient variety, or whatever. So there are many ways to obtain empty stratum, but if you are lucky, then it's non-empty, and you obtain. So once again, you may disregard this general nonsense about functors, and you may just take this representing Grassmannian scheme, and inside there just take the stratum of flatness certification for this particular polynomial phi, and that's it. Okay, so it remains to prove the projectivity of the Hilbert scheme, of the chord scheme. So first, just compose with this T prime into Grassmannian and the Plucker embedding into some big projective space.
Over S.
Over S, yeah, but it will be some whatever lambda field R of this impossible space. No, we already know that it's representable by a locally closed subscheme of Grassmannian. But I announced that it's a projective scheme. So first of all, it's quasi-projective because Grassmannian itself has a Plucker embedding. Okay. So it's a locally closed subscheme in project space. Okay, and second, it suffices to know that it's proper. So to deduce projectivity, to check that T prime is proper by the evaluative criterion of properness. We had this, so namely, yeah, by the way, we don't just know that it's quasi-projective, we from this see that it's separable. Because any closed subscheme in projective space is separable, and any open subscheme is also separable. Okay, and then by the evaluative criterion of properness, you have DVR R, and the fraction field is K, and then you have this functor T prime of one spec R is the same as the quad functor applied to the spectrum of R. Okay, but there is also the quad functor applied to the spectrum of K. Okay, and there is a morphism. You can restrict from the spectrum of R to its generic point. So there is a morphism like this. The separable means that it's an embedding. So you can restrict. You have a family over this disk, so to say, and then you restrict it to the punctured disk. Okay, and the separable means that you can extend from punctured disk to the whole disk at most one way, uniquely. And now we need to check that it's also a surjection. For validative criteria of properness, we need to check that it's surjective. That's an isomorphism.
The uniqueness follows from the validative criteria of
Properness, yes.
separable.
So separable, yes. So need to check surjectivity. Okay. And this is done explicitly by hands. So you need to extend somehow through the puncture. So what do you have? You have this surjection from E over the spectrum of K onto F. And now there is an embedding from spectrum of R into spectrum of, from spectrum of K into spectrum of R. It's called J. So you can take E over R. So ER itself is extended because it's just the pullback of vector bundle over the base. Yeah, there's no problem. You have to extend this quotient. Yeah, and ER maps into the push forward of ER, and this maps into the push forward of F. Okay, and you take the image of the composition and set, well, FR is the image of the composition. Okay, and you have to only to check that it's flat. Okay, and this follows from the fact that over spectrum of DVR, flatness is equivalent to torsion-free. Okay, and well, this is torsion-free, and the subsheaf is also torsion-free. So we're done.
Could you say how you use validative criterion of properties?
How do you mean?
Because like in our formulation, we had curves and we had
Yeah, because the problem is that when we discussed it, we didn't have schemes yet, and so I used global curves. But instead, you can just use. But I'm afraid we have to leave. Нам выйти, да? У вас урок? Или что? Да, прошу прощения. Pardon me?
You want some morphism
Yes.
to be proper. What is this?
So this is the criterion. So it extends through the puncture in the spectrum of R. Okay, if you want it with curves, you just do the same with curves. So you replace R by punctured curve, sorry, K by punctured curve, and R with a complete curve. If you,
Это очень простой вопрос. Какой морфизм мы вообще обсуждаем? Между квотами.
from quad to S, from quad to S. I don't know. This morphism is proper. For example, if S is a point, then we just prove that quad is proper. Yes.
Значит, я знаю, что если у нас есть проективное многообразие, то оно
Yes.
но наоборот не всегда так.
Absolutely. There are counterexamples. Yes.
Я не понимаю, что такое proper writing.
By definition, it means that it's universally the morphism is universally closed. But after any base change, the image of any closed subvariety will be closed in the base. This definition.
What is a counterexample?
Well, it was something three-dimensional constructed by Chazon. I don't remember, but you can look it up in Hartshorn, for example.
Why we need just to prove that it's projective?
Because it's already in project space. So if you know that it's proper, then its morphism into project space will be proper, so hence just a closed embedding. You know it's a locally closed embedding. If it's proper, it's just necessarily closed embedding. So since we already know that it's a locally closed embedding into project space, then properness guarantees that it's a closed embedding.
Makes sense with its
Closure, yes.